Good morning. Today is December 1st, 2018, and this is the John Chappell Natural Philosophy Society Science Chat. I am your host, Franklin Hu, and we invite you to join our mission, and you can find our website at naturalphilosophy.org, where you can join or renew your membership. We also have discussions in our forums, and you can also find us on social media. We have websites on Facebook and also YouTube as well. And if you'd like to help us out, we are organizing ourselves on Basecamp, which can be found at hq.naturalphilosophy.org. And we ask you to please follow our rules of conduct to treat all participants politely and with respect, and that no personal attacks should be made or will be tolerated. And you can find our rules of conduct, which we reviewed earlier this morning at our website, although I believe this particular link at this moment is not actually working. And our upcoming Critical Thinkers Conference will be on June 26th to 29th at the University of Washington in Seattle, which will be featuring Dr. Gerald Pollack. So today's topic is what is the electromagnetic wave? So I've got a document here from Ian. Ian presented basically this paper on April 14th, so we're not going to really go too directly into that, but we'll just use this paper as kind of a jumping off point to discuss what the electromagnetic wave is. Now, so Ian, so your title of your paper was Electromagnetic Waves, an anomaly or analogy. So first, I wanted to explore with you, Ian. So what do you think? What did you mean by anomaly?
Right, Franklin, thank you. Well, the title was a very slightly amended version of what I had originally suggested to the journal. I think it was something like electromagnetic waves, not anomaly, but analogy. So they just sort of jizzed it up a little by putting these question marks in and exclamation marks. Now, what I meant was that if you consider wave motion generally, sort of wave motion which can be sound, for example, in air or a gas, or water waves, waves in a liquid, for example, you find that they're governed by the basic wave equation, as is the wave in free space, or in the ether, if you prefer, electromagnetic radiation. However, there are some significant differences claimed by mainstream physics when we get to electromagnetic waves. And the main origin of this is really the theory of relativity, where they say that the speed of the wave relative to any observer, irrespective of his motion.
May I interrupt for a second?
I beg your pardon?
Ian, I was wondering if I may interrupt. The screen that you're sharing is very hard to read. Is there anything you can do to enlarge?
Yeah, I'm glad you mentioned that, pal, because I was going to say to Franklin, first of all, I'm not sure if this will help very much, but I've actually sent you the PDF, which is a better quality. Secondly, you might be able to expand that. You see, I'm not projecting this, pal. I possibly could try to do this. Franklin is doing this. So if you substituted the PDF copy for this and maybe increase the size, could we see if that's any better?
Yeah, I can work on that while you're talking.
Okay, well, I'll continue then.
Although although this particular paper is actually not, we're not going to be reading through it, so
Yeah.
it's kind of more of a point of reference for me than for you guys. So if you can't exactly read it, then it's we're not doing anything that requires you to read it at this point.
Because I've made I don't know, a dozen or more slides out on the main paragraphs of this paper, and they're included in the video presentation of the 14th of April this year, which is available on YouTube. So you could have a look at those slides. So this constancy of the speed of light, irrespective of the motion of the observer, would require a modification, in particular, of the Doppler shift formula. So, for example, we have a Doppler shift, well-known Doppler shift formula for any type of wave motion, but that, they say, doesn't apply to electromagnetic radiation, which I contest in this paper. So there are various other things which flow from that. I suppose really what I do is I'm underwriting the whole position with regard to the mathematical description, that the analogy comes from the same equations, the same wave equations, just with certain parameters, like, you replace things like bulk, coefficient of elasticity of volume, or it could be Young's modulus, or the bulk modulus. You replace that with the inverse electric permittivity, and then you replace the density with the magnetic permeability, and you get exactly the same equations. And then I look a bit more into the sort of E equals mc squared, or as I prefer to say, E equals k mc squared, where k might be any value between 1 and a number adjacent to that. And I look at some nuclear reactions and just maybe question the exact correspondence, making that constant equal to 1, and questioning whether that has been determined experimentally. I then look at the ether, and I conceive it as an infinite transmission line with inductive element per unit length related to the magnetic permeability, and capacitive reactance per unit length, capacitance per unit length related to the permittivity. And then in the general case, talking about an additional resistance or resistivity, parallel resistivity, which leads to loss, if you like, and a series resistivity, and a shunt or parallel conductivity, which would lead to a leakage. So it's quite analogous to, say a submarine cable or something like that, transmission line.
But in all your work, just to kind of get to your main point, it's like basically you're saying that the electromagnetic wave is very analogous. I mean, it acts and looks the same way as ordinary sound waves. Is that correct?
I do say that, but I would mention one thing, because you, Franklin, put in the series of proposed questions about the transverse nature of the wave. So my position is I'm not dealing with longitudinal waves which may exist at present. I conceive certain differences. So I would say that the wave is transverse in regard to the electric and magnetic fields, which are varying at right angles to each other, are transverse. So there's a difference there. But otherwise, they're completely analogous.
Well, that would be a gigantic difference, because sound waves are transmitted in a purely longitudinal manner, and we understand that as just a compression wave. Just like we have a speaker, and that thing just pushes in and out. I mean, we know that's the only thing it does, right? That doesn't move transverse, and there's no transverse component at all in a sound wave. Now, if you were to propose that the electromagnetic wave is in fact transverse, this throws all kinds of monkey wrenches into the analogy, because a lot of people would bring up that, well, the only thing that can transmit a transverse wave is actually a solid. So, but the medium of the electromagnetic wave, is it is it back to solid? Some people want to say it is, because
No. Even if a light is a transverse wave, we can travel through ether. It doesn't require it is solid.
Well, I'm just saying that you can't have your cake and eat it here too. You can't say that the electromagnetic wave is analogous to sound waves, and you pointed out that the properties such as the speed of light are very analogous to the same formulas used for the speed of sound, based on things like density and elasticity. But we know those particular things are absolutely based upon longitudinal compression waves, and if the wave were transverse, that would be a completely different kind of wave.
Well,
going through
quite
a
see the point
completely
you're
different kind of medium.
Yeah, I quite see the point you're making, but I would maybe answer it at least partially in this way. In a compression and rarefaction wave, you have the air or the gas which is being compressed and decompressed, and you're getting this variation, and that's resulting in the sound wave. Now, I would conceive of the ether as, if you like, a material or quasi-material substance, which again is being analogously compressed and rarefied. Now, the compression is taking place in terms of the magnetic variation, and the rarefaction. Well, it's a combination of the electric and the magnetic variations. Now, these are occurring transversely, because I think there's experimental and theoretical reasons to believe that. But what I do, and this is, I'm trying partially to answer your objection, I conceive of the pointing vector, which is the vector product of the electric field intensity and the magnetic field intensity, which is basically the power of the wave, which actually indeed is moving longitudinally. So it's only really the sort of variations, the analogies to the compressions and rarefactions, which are not occurring longitudinally, they're occurring transversely to the wave. But the wave, the power in the wave, the watts per square meter, are actually moving exactly in the same way as a sound wave would.
Well, I'm going to sort of put forth.
So you mean to say that light waves are longitudinal waves instead of transverse waves?
Well, I'm going to put forth my contention, which is that I would take the electromagnetic wave analogy even further by saying that my question is exactly this: is an electromagnetic wave really transverse? My opinion is that is false. That in fact, the electromagnetic wave, the only way it can have so many similar properties to the sound wave is if it actually is transmitted in the same manner, which is through a compression type longitudinal wave through a medium which is made of particles. So,
Harry, are you able to see on your monitor when people raise their flag so that they can cut in a easy manner?
Yeah, I can see it. For example, Harry has raised his flag, and I was about to give him permission to speak.
Right. Okay, because he's had it out there for a while.
Yep. So as soon as I was going to get done speaking, I was going to do that. But as our new rules state, please be very careful about interrupting whoever is currently speaking. At least give them a pause. Please don't just speak right over them, okay? And you can also raise your flag, and I will get to you. So, Harry, you had a comment, and then Jim.
Okay, my question to Ian is I don't really understand what Ian's saying. So, Ian, as I understand what Ian is saying, and I'm asking for a clarification if possible, You're saying, as I understand it, that relativity presents a problem for the concept of electromagnetic wave because it denies the existence of a medium. Is that what you're saying? That's what I thought I heard at first. That's my question.
But relativity is actually a wrong theory.
Well, okay, let's put that aside for the moment. But yes, Harry, I didn't actually express it in those terms, but that amounts to the same thing. I mean, in the absence of a medium for transmission, which I suppose will give you a frame of reference for the motion of the wave, well, then you have to modify the equations, in particular the Doppler equation. And the Doppler shift is only dependent upon the relative velocity between the source and the observer. So if you have a source moving towards an observer, say we're talking about relative to the Earth, it will give the same formula as an observer moving toward the source. Now, that is not the case for any other form of wave transmission. The Doppler formulas are slightly different. In one case, it's like v plus u in the numerator. In the other case, it's v minus u in the numerator, and v minus u in the denominator.
Well, I thought that the Doppler effects were exactly the same for electromagnetic waves. I mean, we obviously that's definitely one way we measure velocity from, say, our satellite probes is by looking at the Doppler and the electromagnetic wave. So I don't understand when you say that there's some kind of difference between sound wave and the electromagnetic wave. I think those two are actually completely equivalent, aren't they?
Well, imposing upon the eyesight to read these very small things, equation 30 of my paper gives the accepted Doppler shift for sound waves, for example. But equation 31 gives the accepted formula for electromagnetic radiation. They're different formulas.
I'm not sure how that's possible, but let's go look at your paper here. 30 and 31.
So the 30 is the well-known Doppler formula. FO is the frequency of the observer. FS is the frequency of the source. C is the celerity or the speed of the wave. And VO is the speed of the observer, and Vs is the speed of the source. That's well known. But that, so they say, cannot be applied to electromagnetic radiation. Now, I'm contesting that. I think it does apply. But the problem with that is you can you find that the speed you see, I just read it here so I don't get it mixed up. If you have only the source in motion, well, then the observed frequency and the wavelength and the observed wavelength vary, while the wave speed remains constant. However, if only the observer is in motion, well, then both the observed frequency and the wave speed vary, while the wavelength remains constant. Now, that second bit there would contradict the second postulate of the special theory of relativity, were to apply, where the same formula to apply to light or electromagnetic radiation generally. So therefore they modify, it's well known, you can look up any book on relativity or any physics book, and they get equation 31, which, by the way, I'm contesting. I say it's wrong, but I'm just telling you what they say. And I'm suggesting an experiment to show which is right, actually. It'll be quite simple. I say you should do two experiments. One where the source is moving only, and another where the observer is moving only. And the theory of relativity would say there would be zero frequency shift because it's totally symmetric. Whereas the classical formula for sound would give equation 32 in my paper, which would give a small difference, which is approximately v squared over c squared, beta squared. It would be a costly experiment to do because I think you'd need things like maybe a tenth of the speed of light for the motion. But it could be done by satellite transmission. But I believe it's unnecessary to do this. In fact, I think I would have as much success. I think I said this at my presentation. Dr. Carl Zapfi, Harry well knows this, proposed to NASA that they do a Michelson-Morley experiment in outer space, and he didn't even get the courtesy of a reply. I'm suggesting this sort of experiment to show which is correct, the classical theory or the relativistic theory. Now, I'm sure if I wrote to NASA and asked them to do this, I wouldn't get a reply either. But nor do I think it's actually necessary to do this, because I think the theory and the existing experimental evidence we have already, and by the way, I'm relying upon things like the Romer observations of the eclipse of Io, the satellite of Jupiter, not only when the Earth and the Sun and Jupiter are in a straight line, but when there's a right angle between them, when they're in quadrature. Those experiments, and also the Sagnac experiment, which actually both of those show, if you like, a c plus or minus omega r, where omega is the angular speed and r is the radius vector, the distance from the origin. So both those experiments show that.
So the only difference between 30 and 31 is the square root term.
Yeah, I haven't actually derived it, but in Einstein's 1905 paper, which you could get on the web if you wish there, you've done it before, he actually does that. He says that formula, if we plug that in, we get the interesting equation, and he with the square root there, v c plus v over c minus v. Or I think it's sometimes expressed as 1 plus v over c over 1 minus v over c. And the reason for that is c plus or minus v is sort of a heterodox thing to express in any formula, so it's better if you disguise it. But you effectively get the same formula there. I don't know, it might be worth actually getting up the Einstein paper and just having a look at that bit. He has it towards the end of his paper where he has sort of not the kinematic part, but the sort of optical electromagnetic part.
Yeah, all these things tend to confuse me. Although, if you're thinking that the electromagnetic wave is completely analogous to the sound wave, then Einstein's postulates themselves are not that confusing, because it's just saying that the speed of sound is independent of the transmitter or the receiver, which is intuitively obvious in the case of sound, right? There's no problem with that.
Right. If you omit one word, delete one word from what you've said, you're perfectly correct. So in other words, the second postulate, in the way it's originally expressed, says that the speed of light is independent of the speed of the source. That is correct for sound waves as well, because the speed of if you have a moving source in the static medium, you still get the same speed of sound. And it's true for water waves as well. Now, so therefore, it is true for electromagnetic radiation. But unfortunately, what they've done, and what he does later in his paper, is he extends it to complete reciprocity. So he says, well, it's not only irrespective of the speed of the source, it's irrespective of the speed of the observer. Now, that is manifestly untrue. Both.
No, that I would agree with that. I would say that's manifestly true, even in the case of sound waves. It doesn't matter if you're in a car. If someone sets off some explosion somewhere and you're in a moving car, the speed of the sound wave is remaining physically the same. I mean, I think that this is the part that I have a problem with relativity, that people interpret that as meaning that it is different. I mean, the actual I'm thinking that what Einstein said, and this is my little stick on relativity, is that if you go strictly by what Einstein says, Now, Einstein did not say that the speed of light is the same relative to all inertial frames, which is how a lot of people frame it. But Einstein didn't say anything of the sort. Einstein said that the speed of light remains constant, independent of the sender or of the receiver, meaning that, physically it retains that same physical speed relative to the medium, which can be defined by any inertial frame, meaning that there is a special frame, in the case of air, the motion of the air. It could be, and that, it could be like 500 miles per hour, and the speed of the sound wave remains 500 miles per hour, even if you're moving relative to it.
But the Sagnac experiment, for example, Franklin, where you have a ray of light which is emitted, and then the receiver, the observer, the receiver is actually moving towards it or away from it because you're on a spinning disk. Well, that actually shows that the speed varies from the observation point of view, from the point of view of the interferometer or the camera.
Yeah, this is the main point. It depends on where is your point of view. As some Jedi say, what you believe in depends greatly upon your point of view. Now, this actually really only makes sense in the laboratory frame, where you have to pick something which is stationary. And in Einstein's paper, he mentions the word stationary about 50 times, because it's very important that you measure things with respect to the stationary frame and not with respect to the moving frame that you might be measuring from. So I think that's an important difference. My point being that I think that the electric wave and the magnetic wave, the electromagnetic wave and sound waves actually observe Einstein's postulates as well, I guess is what I would say. That everything that you could say about...
Sorry, where you say that irrespective of the observer's position. I mean, that's experimentally known. You gave an example of a motor car moving towards an explosion. Well, if you're moving towards the sound wave...
If you're moving towards the sound wave, but if you're still measuring things with the laboratory frame, which would be the frame of the Earth, then you would clearly measure the same speed of sound no matter how fast the car is traveling. It's relevant because you're not measuring it from the frame of the car.
That's correct. Maybe we're speaking at cross purposes. That is correct. But what I'm saying is, measuring it from the point of view of the moving car, you will get an increasing speed.
Yes, you will get an increasing speed from the point of the car. But Einstein never said that, is my point.
Well, whether he said it or not, I think 99%.
That's how people interpret it, though.
Relativists say that.
That's how people, like I said, my bone of contention is that's how people interpreted that. And that they're saying that the speed of sound should remain the same measured from the moving car, no matter how fast the car is moving. But that is, of course, complete nonsense.
Yes.
But Einstein never said that. His postulates just say that the speed of light travels at a constant rate relative to a stationary frame. And in taking in that's exactly what we would expect in the case of a sound wave, which remains the same speed relative to a stationary frame, which is the Earth. So I would say that...
I know we have discussed a lot of this before, but he does indeed start his paper, his 1905 paper, in the way you express it. But when he gets to the latter part of the paper, he actually departs from that. And in particular, that Doppler formula with the square root, he says, since it's only the relative speed, Vs minus Vo, which determines, it's completely symmetrical. Therefore, we have to modify the formula. And this is the formula you get. So he seems to depart from what you say, although he starts on that basis indeed.
Okay, well, that's news to me. I'll let you know. I think Jim had his flag up. Does anyone want to make a comment?
Yes, I do.
Go ahead.
First thing to point out here, Franklin, is that what Einstein said he basically contradicts himself in his paper, and that's kind of the issue of a lot of the confusion that you have expressed. And Ian is trying to point that out. He tried to point that out, okay? And this whole issue about the independent of the source, okay, that can't be, because when he derives the Lorentz transforms, he doesn't use that assumption in doing that, okay? So anyway, there's a point of confusion there. So I think arguing or discussing what Einstein said or what you believe Einstein said is kind of not really going to get you anywhere, because what he said, according to Roger Anderton, you know, Roger Anderton says it's all ambiguous, okay? And so you're just arguing about something that's unclear, vague, and ambiguous, and there's really not much point to be gained by doing that.
Yeah, I don't want to get into a relativity type discussion. I think we should just frame it in terms. Yeah, well, I think we should term in terms of what we actually believe happens. So I'm contending that no matter what Einstein says, that the speed of light is like the speed of sound, in that it is constant relative to its medium. The speed of its medium actually determines its actual physical speed.
Well, I think Ian is proposing an experiment to try to resolve this difficulty. At least that's my understanding of what he said.
Yeah, he's trying to resolve some difficulty. He doesn't particularly believe in this equation 31, and probably neither do I. I would try to argue that whatever you can find for sound waves, you should find for electrodynamic waves as well, eventually. So, Bill, looks like you've raised a flag.
I was going to comment that there's a difference between a fluid, which is composed of particles, and the electromagnetic field, because the field is the source of the particles. So there are places in the universe where there aren't very many particles, and but yet the tensile strength of the field is there, and it still supports waves, even though there are no particles. And so how do we address that?
Well, that would be a fun. Oops, someone's got a. Please mute yourself if you're not speaking. Okay, yeah. Otherwise, we get a big echo. Yeah, that would be another question. It's fundamental to the question of what is an electrodynamic wave, because we know that a sound wave does require particulate matter in order to transmit. So if I create a vacuum, we find that sound waves cannot travel anymore. Now, but if we say that an electromagnetic wave is exactly the same thing as a sound wave, then we would have to say that there must be particles in space to do the transmission in a similar manner, right? So, or you say that the electrodynamic wave is something utterly different. You know, for example, Ian mentioned that maybe it's the rarefaction and compression of, say, the magnetic or electric fields. Although, what would you mean by that? I mean, how can a magnetic field be compressed? As in, we don't normally measure it as that way. But, you know, that's a different way of thinking about it. And that the mainstream would say that the electromagnetic field doesn't require a particulate medium to transmit. But then, like, if it's not a particulate medium, then you have to figure out this other exotic way for a wave to travel, right? If it
put myself in the queue, Franklin, could I put myself in a queue, because I can't get a flag up right now? I'm on my phone. Can you hear me okay?
You're very quiet, Cornelius. Can you speak up?
I'll try to get onto a different system, and I'll try to get into a different system and put myself on the queue. I'm on my phone right now. The sound's a bit bad, so I'll just sign off, see if I can get better sound connection.
Okay, we can kind of hear you, but you're very, very quiet.
No, I just wanted to put myself in the queue because I'm on the phone. I can't get the flag up.
Well, why don't you go ahead and make your comment? I think we can hear you well enough. Just speak as loudly as you can.
Okay, my comment was towards the direction of the medium that the waves are moving in, and basically it goes back to the sound waves not adhering to the Einstein's theory of relativity, and basically media is, as Bill is saying, is a continuous electromagnetic carrier media, and it carries electromagnetic waves. But all matter that we know of, if it is composed of geometries of electromagnetic waves, that are like particles are focused geometries of electromagnetic waves. So in a sense, when we're looking at a transmissive electromagnetic wave like light, we're looking at that wave's motion relative to a focused electromagnetic wave like matter or mass. And so they're both waves traveling in the same media. They're the same. And so what you've got, if you were to look at it this way, from a sound wave perspective, which is strictly longitudinal, then, if you were to look at a sound wave traveling in a horizontal direction, and you were to look at a sound wave traveling in the same media in a longitudinal direction, or in a perpendicular direction, where the vector pointing director of the sound wave moving in a horizontal direction would be relative to if you make a line along that direct path, and then you take the sound wave that's traveling perpendicular to that, since the two are traveling in the same medium, they're both affecting the characteristics of that medium, and the waves will cause each other to curve in that medium, or the one wave interfering with the other will make it look as if there's not a straight, it's no longer a straight line. So that's where you have a sound wave relative to a sound wave is consistently the same speed. Relative to a solid, to a object, which is a focal point of a sound wave, they would be different, because the focal point can actually maintain a fixed location, where the sound waves can only maintain vector directions that can change each other. So that's kind of how it would be for a sound wave analogy. In my view, the media is a continuous solid, which is basically the same thing I think that Bill is saying. He's not really saying it's not a particulate media. The particulate particles are basically a pattern of waves in the media that make the particulate characteristic. That's basically my summary on it.
Okay, so Bob, you've got a comment?
Well, I wanted to go over the standard derivation and classical electrodynamics for the wave equation and point out some issues that I've had. And part of that would include showing that really there is no transverse waves in electrodynamics.
Okay, so Bob, I'm going to promote you. So now you should be able to, there should be on your bottom of your screen a share button, and you should be able to share your screen. Let me see, I think I have to unshare my screen. So we should be able to see what's on your screen. Are you able to find the controls?
Yes, I clicked on shared screen.
Okay, we can see your screen now.
You can. Wow. All right, so where the heck is it?
Well, I can see your screen.
I cannot tell what you can see, so I can't tell if I need to make this bigger or not.
Oh, well, I can see it. It looks good. I see the derivation of the wave equation, and we can see that. So what do all of these symbols mean? I mean, all of this looks like complete Greek to me. What physically does this stuff mean?
Exactly. That's kind of what the question is.
I don't know how much I want to go into that aspect of, for example, equation 1 is the divergence of the electric field versus the curl in equation 3 of the electric field. And what does all that mean? Rather, what I was going to do is a very quick review of what I find as a standard derivation of the wave equation in Maxwell's electrodynamics. And it seems to start with assuming that Maxwell's equations are valid. And I've listed the 4 Maxwell's equations. Then assume that there are no charges at the point of interest, at the point that you're going to measure the wave, which takes out the free charge and the free current densities. And then from there, we take the curl of equation 3 and use a vector relation to get this equation and exchange the order of the spatial and time derivatives.
So, but what do you mean by assuming that there's no charge present? Because we have Maxwell's equations.
Yeah, at the point, Maxwell's equations, at the point of interest, is there any charge? That's this rho sub f, that's the free charge density function. So at the point of interest, is there any charged particle there? If there is, then rho f is the charge value per volume. And if there isn't, then you're in free space at that point, and that is 0.
Yes, so I would think that if there's no charge present, that all of these equations should be 0, right?
Well, the divergence of the electric field would be 0. The curl doesn't have to be 0. So anyway, back to the derivation. Using Gauss's law, which is this here, the divergence of the electric field is 0 in vacuum. In this equation, this is where we're at so far. This term goes away, and you get the Laplacian of the electric field is equal to this time derivative. You can use Maxwell's equation 4 then, which is the curl of the magnetic field. Substitute that, and lo and behold, rearrange terms, you get what they call is the field equation in vacuum. And I have problems with that derivation, lots of problems. So my first problem is that it's assuming Maxwell's equations are valid. And this assumption does not hold up when trying to derive these equations from fundamental principles. The fields should also be connected to the discrete source charges. Because that's what you're playing with. That's what we have, is discrete source charges. And then you can do level of abstractions in the mathematics. You get potential, scalar potential functions, vector potential functions, and from that abstract to another layer, and you get the fields, the electric field and the magnetic field. So assuming that Maxwell's equations are correct, I think is problematic right from the start. So
now, I don't quite understand that again. Why do you think that those, I mean, those are empirically measured, right? So what can be wrong with those?
They are not connected to discrete source. So let me see. This removes all sources. Okay, assume no charge. Right. So in the standard derivation, you assume that the point of interest, there are no sources. However, waves do not exist without sources. Even in space where there are no charges, the waves must be tied back to the sources that generated them.
Now, I can understand this as like you can only have an electric field if there's an actual charge present. And now in the case of an electromagnetic wave, the charges that generated that wave are like 1,000,000 miles away, and that there's no actual charge anywhere near the transmitted wave.
But the equation should reflect that, and that's where time retardation comes in, or time delay. So the charge that rho f should always be there, but time delayed. That should never be zero, because when it's zero, you have disconnected the source of the wave in the wave, and you just physically can't do that.
I see Bill have a flag up. Did you want to say something?
I was going to say that we have experiments that show that structures, which we call charges, are constructed of the field, and where there was no charge before, we can make a charge entirely out of the field without introducing more charge. And so it seems that experimentally we cannot say that the charge is the source of the electromagnetic field, that we have experimentally shown that that's not true. And so what happens is when you do the when you make a charge out of just the field, that charge is a structure like a hurricane or a tornado, and it has a very large effect, but it doesn't go to infinity. And we seem to find in space where we have an extremely low charge density that we have fields that are too strong to be from those charges.
All right, I see Ian. Ian has a comment.
Yes, thank you. It was basically in response to Bob's points, which I think he's continuing to make. Yes, well, what I have actually done is gone a bit further. I have dismissed any extraneous charge density associated with the wave, but I have included a conduction current, a current of conduction. So I haven't, made that zero. And what that actually introduces is if you if you take that equal to something like J is the current density, or JF if you want to call it, equals sigma E. Now sigma is the conductivity of free space. So basically Einstein takes that to be zero because there's no ether, so that disappears. But you see, I include that. So in my full analysis, I don't just get the wave equation without any dissipation. I get the wave equation with dissipation. So something like the second partial differential with respect to space is equal to 1 over c squared times the second partial differential with respect to time, plus a constant times the partial differential with respect to time. In other words, the first order derivative as well. So there's actually a dissipation in the wave. It's not an idealized system which has no dissipation in it.
That's very interesting, and why I would very much like to read your paper. I do see in my email that your paper has arrived. Thank you. I will enjoy reading it later this afternoon.
And thank you for that. If I may say that, if you look at the references, you'll find my first paper, which actually goes into this very point in more detail. And you can download that from the index of the GED. If you have any difficulty, you can let me know.
So Ian, are you saying that from your derivation, the electromagnetic wave shouldn't exist for very long? It should decrease. It should have a short distance.
Okay, that certainly is relevant because it does decrease exponentially, Franklin. But in the case of electromagnetic radiation, it's not a short distance. In the case of sound waves, it is. So, for example, if you have sound waves of 1 cent, I'm reading from my paper now, 1 centimeter wavelength, corresponding to sound in air at about 30 kilohertz. Well, the amplitude is reduced in the ratio of e to 1. Well, what I've done is I've taken this Italian physicist Monti, who's a dissident physicist who's done some calculations on this, and he's included this dissipation term which is effectively a tired light system, and he's plugged in some values of the diminution, of the increased redshift with increasing distance. You know, assuming that the Hubble law is not the correct law, but that you have an exponential decay. And he's curve fitted this, and he got a value of this. It's something like 2.85 times 10 to the minus 29 Siemens per meter. Now, if you then plug that in, well, then into the formulae for E and H, well, then I estimate that the amplitude will be reduced by E to 1 after traveling a distance of about 10 gigalight years. So it's a very, very long distance. That's why it hasn't been noticed, really, the dissipation of the ether, because it's very, very small.
Okay, we got another comment from Harry, and then we have to go back to Bob.
I've got a question for Bob Gray. Bob,
Yes.
could you summarize what I agree with you? First off, the claim that Maxwell's equations are correct, and starting from there is basically an assumption, okay? And it's something you have to take on faith. You're saying you don't agree with that. Okay, I accept that, and I tend to agree with it. What is your conclusion? I mean, could you summarize your conclusion?
My conclusion is that Weber electrodynamics is more mathematically complete and accurate description of classical electrodynamics. And I won't go into that in this little presentation, but let me continue, and I'll show you why I'm coming up with that. In the end, I'm saying that there is no electric field, there's no magnetic field. And I'll show you that in the end here, just real quick. So
Well, Bob, let me just point out to you that what we're talking about is a model, and electric field and magnetic field are conceptual concepts. And whether they exist in reality or not is, kind of argumentative, I think. Is that what you're saying, or are you saying something different?
I'm saying that we're focused an awful lot on wave equations for an electric field and a magnetic field, and I don't think those things physically exist. What exists instead is a potential energy from the charged particles. That's the fundamental physical reality of what's going on. And then if you can describe its characteristics by mathematics, then you come up with these level of abstractions which lead you to the concept of an electric field, a vector, and a magnetic field, a vector. But those are not the fundamental things. The fundamental things is a scalar potential energy. So I'll show you in just a couple of slides.
Yeah, why don't you go ahead with your presentation, and
So
we'll hold questions until you're done.
Okay, looking at Jackson's book, I'm going to go in reverse order of Jackson for a particular reason, which you'll see in a minute. On page 239 of Jackson, he has the electric field defined by the gradient of the scalar potential, and the partial time derivative of the vector potential function. This is the most general definition that I find in Jackson's book for E, the symbol E, whatever we're going to interpret that as eventually. And this should always be the starting place if you're going to be talking about electric fields, magnetic fields, is this definition. However, earlier in his book, he uses E as this, just the minus the gradient of the scalar potential function. Well, if you're going to do that, then really what he's done is taking the partial derivative of respect to time of this vector potential, he's setting that equal to 0. He must show that explicitly if he writes the equation E is equal to minus the gradient of the scalar potential. No, it doesn't, unless you impose a restriction. And the restriction in this case is this partial with respect to time. Or on page 29, he shows the divergence of the electric field is equal to this charge density function. So Gauss's law, that's incorrect the way he expresses it in this equation 1.13, because he does not include the restriction of this partial derivative with respect to time. Must be 0. Okay, if you include those restrictions, I have no problem. But he doesn't include those restrictions. And when he writes Maxwell's equations, he doesn't include those restrictions. And that's why I say the assumption that Maxwell's equations is mathematically correct is an assumption, which I'm pointing out is not a very good assumption. So if you use this assumption or this restriction, the partial derivative with respect to time, the vector potential function is equal to 0, and then look at Faraday's law, lo and behold, Faraday's law must be equal to 0. The curl of the electric field must be equal to 0. And there again, Maxwell's equations seems to be failing. Or I've seen it in the textbooks where they say, no, 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 that's not what we're doing. What we're doing is imposing the Lorentz gauge condition in which the divergence of the vector potential is equal to 0. And I say, okay, that's fine, but then you must write Gauss's law as the divergence of the electric field is equal to the charge density function with this restriction. And with that restriction, you are specifying a particular gauge. So your gauge freedom of Maxwell equations, Maxwell system, goes away. If you work in some other gauge, this Gauss's equation, which I'm showing here, is not valid. And so again, if you're developing wave equations for E and B fields, and assuming Maxwell's equations are correct, I think you're going to have a problem. So the best resolution, in quotes, best, my opinion of what the best resolution is yes, to start with the most general definition for the electric field in terms of the scalar and vector potential, as Jackson has in his books. But then note, you can just as well define a symbol, which I say E super C, meaning the Coulomb part, and then write Gauss's law as the divergence of the Coulomb field is equal to rho. And when you do that and try to derive the wave equation, as I showed earlier, you can't do it, because now this is, you know, EC, not E. And so the derivation of the wave equation is not right in standard Maxwell. I want to point this out. In Weber, the force on a charge, these circles are charges, due to another charge is in the along the line connecting the two sources. I mean, the two charged particles. So if you have like a dipole antenna and this source is moving up and down this dipole antenna, just take a look at the top, the force, which is a vector towards that charge, is going to oscillate in its direction. But you can break that force up into a tangential component. Divide that by the charge, and that's the electric field. But what's really happening here is the potential energy, a scalar function, and that's moving with the charged particle up and down this antenna. It's only the projection in these transverse directions do you get these transverse electric field and I suppose the transverse magnetic field, if you want. So essentially, particularly in Weber, all Weber's electrodynamics can be derived from this Weber potential energy function U, which I have not shown here, but I have it if anyone's really interested. And a change, a spatial change, the derivative of the potential energy equation with respect to the spatial coordinates gives the force. Okay, we'll divide the force by the charge. There's your electric field. But it's really all coming from a scalar potential energy function. And it's that scalar potential energy function which is oscillating and changing as you move the charges, not electric fields and not magnetic fields. And with that, I'll shut up and not take so much time. Happy to answer questions.
Okay, we have some questions, although, Bob, I would have to admit that about 98% of that went right over my head. But so, Paul Schrodinger, you have a question? Or Cornelius, you had also, you had your flag up? Bill, did you have a question or comment?
Yes, I have a comment. The derivation of Maxwell's equations in the book you're citing is not valid because it is in terms of the vector potential instead of the energy potential. And the vector potential, del dot A, is supposed to be equal to 0 in order to get the solutions that they have there. And it turns out that the existence of magnetic monopoles shows that del dot A is not equal to 0. And many of us have magnetic monopoles on our refrigerators. We call them refrigerator magnets, and we don't even know what we have there. But they are for sale on the internet, and you can buy them and test them, which I have done. And you can see that they are not dipole magnets; they are monopole magnets. And so that's one question. The other thing is there are 6 empirical equations of electrodynamics, and when Maxwell was solving them, he solved all 6 simultaneously using a kind of matrix technique. But after he died, Oliver Heaviside redid it in terms of vectors, and he didn't like all 6, so he just used 4 of them. But the 6 represent the summary of the experiments that have been done in electrodynamics. And so when you ignore certain numbers of experiments because you don't like the solution you get, that's not the way to do science. And so in my book that I published on the universal force, I showed what the solution is if you use all 6 of the equations with the energy potential, not a non-physical thing called a vector potential, which has nothing to do with physics. And
I agree with you, Bill. And I am going through your books still. And in this Weber approach to electrodynamics, it starts with that potential energy equation. And yeah, it's curious.
It's not just a
I see Jim. You raised your flag. You have a comment? Jim?
Hi, can you hear me?
Yes.
You're breaking up a little bit, but go ahead.
Yeah, I just wanted to point out that when we talk about transverse wave, and it's brought up that a liquid cannot support transverse wave, there's a thing called liquid crystals where the liquid behaves like a solid and voltage or electric field is present. In other words, they don't intrinsically have to have this transverse elasticity when there's no field present. But the instantaneous presence of the field can modify the behavior of the medium to support the transverse wave. Does that make any sense to anybody?
Well, I didn't hear it well enough. Something about liquid crystals and having it applied to a field and something in a transverse.
In other words, when there's no field present, the liquid is a liquid. It doesn't have a transverse stress like a solid. But when the field is present, it changes its behavior. So you don't have to have it. You don't have to have a solid medium to have a transverse wave, where the whole medium is quote unquote a solid. There's been a problem with ether theories from way back. Does that make any sense to anybody?
Well, it sounds like you're talking about polarization, because that's what happens with an LCD display, and that when you activate the liquid crystal, it becomes a polarizer, and that's what we observe as the lights either become blocked or transmission. But I don't think that has anything, but it sounded like you were saying something that you can have a transverse wave through a liquid because of these liquid crystal displays. I'm not sure that makes any sense. Is that what you're trying to say?
I'm only talking about it as an analogy. That you don't have to have the whole medium always be solid in advance. But as the electric field advances, it instantaneously, for the moment, transforms the behavior of the medium to support the
All right.
behavior.
So, Ian, you have your flag raised. Do you have a comment?
Thank you, Franklin. Just perhaps a couple of points, basically for following from Bob's. Well, first of all, just generally, as you were giving this, I did actually see some similarities with Bill Lucas's work and on scalar potential and the alternative use of Weber's potential energy and so on is interesting. I'll have to look at that in a bit more detail. But maybe one or two other things. Using the Maxwell equations, or rather the Maxwell equations modified to allow dissipation in the ether, you do get quite analogous results to that of what is known in transmission line theory and experiment. You get exactly the same equations. And in fact, I pointed out that these equations were basically used in designing the transatlantic telegraph, or four of the telegraph lines in the middle of the 19th century. So it's well known. Now, just one or two other points. I also introduced something else which is known. Rather than use partial time derivatives, I use the total time derivative, which includes the convective term. Now, this is done in hydrodynamics all the time. It's well known. So I don't really know why it wasn't done in electrodynamics, where it's really a singularity. I mean, Hertz showed
the original equations of Maxwell's in the quaternionic form, it's my understanding, included a convective component, and that's one of the things that Heaviside threw out when he converted it to vectors. And that I get in a book on the history of, I think it's the Maxwellians. I forget the title of the book.
Well, I must look at that again, Bob, because I have Maxwell's 1873 text, and I have the quaternion formulations, but I didn't actually see that. So I must look at that later, because my understanding was that Maxwell didn't do that, and Heaviside didn't do it when he changed it to vector notation. But it was Hertz who's frequently considered an experimenter, but he was a theoretician as well, who actually introduced the convective term. But anyway, whoever introduced it, it does render the equations invariant, and therefore, there is no necessity to introduce the Lorentz equations to make the equations invariant. And just one more point I'll just mention, just for your titillation in a way. I mentioned this free current density sigma, which is the conductivity, E, which is the electric field intensity. Now, there's also another thing. If you wanted to make the equations symmetrical, you would also have another term, which I've just coined the term here. Let me see what I call it. The conduction current density vector. Well, then there'll be another term which one could call an obstruction voltage density vector. Well, here I'm relying upon, to a certain extent, the conception that a so-called conductor of electricity is a facilitator and also an obstructor. And that value is actually rho h. Rho is the resistivity, and h is the magnetic field strength. And in general, that actually exists as well and should be included in the Maxwell equations. But you will find that for very high frequencies, that term reduces to zero. So at electromagnetic frequencies, it is approximately zero. So it actually needn't be introduced. But if you were to write Maxwell's equations in the most general form, not only would you have a sort of two terms in the curl equation for H, but you would have two terms in the curl equation for E, and it would be an obstruction voltage density. So I just thought I'd mention those 2 points, and thank you for the other bits as well. Thank you.
Okay, Harry, you have a question?
Real quick, Ian. I have the book The Maxwellians by Bruce Hunt in front of me, and in the appendix, that would be page 245. He starts giving Maxwell's original equations and comments and shows what Heaviside changed. And in part, he says that Heaviside, by restricting B to be the case of the stationary medium so that the velocity is equal to zero, Heaviside took the effect in motion, blah, blah, blah. Anyway, he's saying here, if you want to look at it at some point, that yes, Heaviside is throughout a medium motion from Maxwell's original equations.
Okay, so Harry, did you have a comment?
I got lots of comments. I don't think we're talking about electromagnetic waves as we're talking about theories of electromagnetic waves. And I guess the discussion is kind of confused. Bob, I would go back to the Maxwell's equations. Let's go back to your Maxwell's equations.
Well, not my Maxwell's equations. I wouldn't use them.
The ones that you put up there, you put them up there.
Of course, go ahead.
Okay, the point I wanted to make here is that, there's lots of different interpretations of these equations. I personally object to the form of the equations and the way they're written, okay? And there's all these different ways of writing the equations depending upon the units that you choose.
Yes.
Okay, you're aware of that. And then I object to the idea that B is magnetic field. Okay, so you can object to that. I object to this putting in the conduction current part here in the curl equation, because that means, according to some people, that you're counting the displacement, the current twice, because you've got the current on, you've got a two-term part, so you've got two different currents or two different concepts of what current is. Does that mean you're counting it twice or once, or, so the bottom line is what we're talking about here when we're deriving things from models it really depends on your assumptions in your models and your theory about what the model is trying to express or prove or demonstrate, right?
Right, I agree.
So, you know, I'm not really sure we're going to get any agreement based on going from a particular set of equations or a particular model. Now, what Franklin, you know, comes in, he says, well, I don't really like this. I think it's a longitudinal wave. Well, you know, I mean, that's assuming, you know, that you have the idea of what it is, you know, based on your theory. And so then you're going to argue, you know, because you have a theory, so you're starting from your theory. Science is supposed to be based on experiments, and we're supposed to infer things from the experiments, but we're not doing that. We're inferring things from theoretical constructs that are couched in equations. And then you can argue about what these equations are or are not to be. So I think we should be talking about what the experiments are and what we think we're inferring from those experiments. Now, to go back to Ian's paper in the beginning, I noticed he had the Sagnac experiment in there. You know, there's a big discussion going on the discussions groups about, so one guy comes in and he says, I think the velocity of light is respect to the source. And then people who believe in ether, you know, they're going to disagree with that. They say, no, the velocity of light is respect to the medium. Okay. And then they're arguing about the Sagnac experiment. We can't even agree on what the experiments tell us.
Right.
So if we can't agree on what the experiments tell us, and presumably what the experiments are telling us is embedded in these so-called Maxwell's equations, well, we can't really agree on any of that. What are these experiments that lead us to these equations are here? We have no real agreement on that. That's probably more, in my opinion, what we should be talking about.
Right. What I have done is to relied on other people, other researchers, of course, and try to add to what they've done. And what I'm saying here is Ampere did a lot of experimentation and developed an equation for force on two Amperian current elements. And Weber took that along with Faraday's experiments, et cetera, and came up with Weber's force equation based on all these experimentations. And from the force equation, he then generalized to a potential energy equation and found that that potential energy equation gives Weber's force equation, which is based
You still there, Bob?
on all these early experiments. What I find interesting is I can't hear experiments. Yeah, I can't find Ampere's experiments in Jackson's books or the classical modern textbooks on electrodynamics. You know, there's no mention of Ampere's force law and the experiments from which Ampere derived his force equation. So I think you're right. I'm relying on the experiments of Ampere, Faraday, as summarized by Weber. And I wouldn't use this Maxwell equation stuff because it doesn't follow. It doesn't follow from those experiments.
Well, I'm not going to really disagree with that but on the other hand, you know, Weber proceeds from an assumption about the nature of electricity, which is the two fluid theory. And so he says that there are two fluids of electricity, and his theory is sort of predicated, and everything sort of flows from that. So again, you have, you know, a theory that flows from assumptions, and Maxwell's doing the same thing. Maxwell is assuming that there's an ether and that there's something called the electric fluid in the ether, and that is what justifies his using these electrodynamic equations, which involves curls and dells. Okay, and you know, so that is but the problem, in my opinion, arises from the fact that you have to realize that the equations are derived from a particular theory or concept about what electricity is. When the ether went away after Einstein, the Maxwell's equations sort of have no embodiment or justification for why they exist other than the fact that they work. And so to me, that sort of implies a big problem, because you have a theory that presupposes electricity is exists in an ether, but you banish the ether, but you're still using the equations.
It's pretty ridiculous, yeah.
Well, the word electromagnetic wave includes the words magnetic and electric. And those come from these equations. Like I said, Bob, I would admit that like 98% of everything you just said there just went totally over my head. But what I understand is that the electromagnetic wave in the mainstream is always shown as an electric field running transverse to a magnetic field, and that is generally derived from the thing that says that a falling electric field generates a rising magnetic field, and the mainstream generally explains that we get this electromagnetic wave as a alternating electric field, which then generates a magnetic field, which then generates an electric field, which is normally how it's explained. And I guess that's what these equations mean. However, that would only make sense only if the magnetic and electric fields were out of phase, so that we would see the rise of one and then decrease of the other. But it's not shown that way. It's shown that the magnetic and electric field are in fact in phase. And so that to me completely does not make any sense, that the magnetic and electric field would rise and fall at the same time and both having a 0 point, because that intuitively contradicts all those other initial empirical results. So to me, that says that whole electromagnetic wave thing is complete phooey. So
I don't think you have any right to conclude that, Franklin. You just don't understand it. Okay.
Well, that could be, but I understand you understand how the relationship between the electric and magnetic field is supposed to work, right? In fact, I think this is your argument. I think I got that from you,
down,
Harry.
Franklin. I mean, you're trying to, slow down. Okay, the whole idea is that you're supposed to start from experiments. Okay, now the experiments lead you to these Maxwell equations, which are expressed in the context of a particular type of theory about what electricity is. Okay, and then you've got another theory of electricity, which is Weber's theory, which is based upon a different concept of what electricity is. But what the idea is, what they're trying to do, and what seems to be a fundamental fact, is you've got something that has an electric effect, something that is associated with electricity, and then you got something that's associated with something different called magnetism. And they found that they can convert one into the other, and Faraday is famous for doing that because he showed he could convert magnetism into electricity. Okay, and so what you have in this electromagnetic wave concept and the idea of it is an attempt to express the fact that you've got this electric effect, something that is associated with what you call electricity in the experiments associated with electricity. And you've got something associated with magnetism in the experiments associated with magnetism, and they're related. And they're supposedly related through those curl equations, which are based on Maxwell's putting together a theory of electricity. Supposedly, he did it based on what Faraday's experiment showed. So it's an attempt to combine electricity and magnetism and to represent those two things. What we're talking about are representations. You seem to take these things as being literally real. The electric field and the magnetic field are representations. They're conceptual ideas that are an attempt to express the physics that they understand it to be that arises out of these experiments. And what happens is that, and I agree with your statement, these representations and the theories and the models that they've developed aren't really fully and completely consistent. And so there are problems with them. But criticizing the models is certainly a legitimate thing to do, but to just say that's phooey and nonsense and completely, I mean, I don't think that's really a fair thing to do. So I'm
okay.
done.
Well, I'll try not to be so harsh on them. But,
well, what I'm trying to say is when you talked about the problem is with this business with the electromagnetic wave and electricity converting to magnetism and vice versa, that comes out of the experiments that Faraday did, okay? But the problem is with the way they derive the electromagnetic waves, they don't actually connect electricity and magnetism, because as Bob Gray showed, he showed that you only get a wave equation for the electric field and a wave equation for the magnetic field, and there's really they're not connected. Okay, so there's something seriously wrong there. And so they're completely confused. The textbooks are completely confused about how electricity connects to magnetism. They don't really have that nailed down yet. And so they're trying to show you how electromagnetic waves are created based on theories that are more than likely totally wrong and false, and based on assumptions that are probably not correct, and try to convince you that it's so. And you're saying, oh, I'm not convinced. Well, I think we've established that their arguments aren't very convincing.
Yeah, so if it isn't a magnetic or electric field, then what is it? You know, I've always challenged people who believe that the electromagnetic wave is exactly this rising electric and falling magnetic field to show me any experiment that shows that along the length of travel of an electromagnetic wave, can you measure anything time varying in the electric field or time varying in the magnetic field? You'd think you'd be able to do that. So if I had, like, you know, a large
models, Franklin, they're conceptual models.
Well, I don't think they think they're conceptual.
About them as physical reality.
Well, I think they are when they express it like that. It would be a physical reality. I mean, we're talking about physics here. These people literally think that there must be a rising electric field and a decreasing magnetic field along the length of travel.
Well,
that's what
people think and believe in very funny things. My opinion, it's very odd that people actually believe in field lines, that the lines of these fields are real. And when the lines of magnetic field lines cut a conductor, it induces a EMF. I mean, the way some people talk about it and the way that some people express it, etc., they really say that they believe that these lines exist. To me, that's very odd. Yeah,
that would seem to be very odd to me as well. But
again, we're talking about conceptual models, an attempt to visualize something that's physical.
Right.
And if you confuse the reality of the conceptual concept with the physical concept, and you argue that the physical concept is wrong because the conceptual visualization is false, that doesn't help us.
Yeah, well, the question of the day still is, what is the electromagnetic field, and what do we mean by it? You know, is it this thing that the mainstream says, which is it's a transverse wave, it's got electric and magnetic time-varying components to it, and, you know, we're so far discussing that particular concept seems to have a lot of problems.
I think
and if you were to say
model,
well, if you were to say compare it to, you know, Ian's initial paper, which is just to show that that the electromagnetic wave has a lot in common with the ordinary compression waves. And So the alternative is that instead of all of this, all of these equations, is that you just go back and say, well, and this is my contention, that the electromagnetic wave is in fact really exactly the same thing as a sound wave. That would be my contention. So the question is, well, what are the problems with that? So why couldn't the electric field be exactly the same thing as a sound wave, which is a compression wave in a particulate medium? So
I would then ask you to express it mathematically so I could look at your model.
well, I would express it mathematically as all of exactly the same equations that are used by sound theory. And I think, Ian basically did that. He just said there's analogies for every single equation you can find in the electromagnetic wave to sound. I mean, the formats equations are, to express like the speed of sound, just like the speed of light, are exactly the same. And all of the observed things like interference are all exactly the same.
Which is why I'm eager to read his paper this afternoon.
Okay, so Franklin, what we have here on the screen is this thing where Bob Gray is talking about because I understand what you're talking about. You're saying that there's just a scalar, right? That's a wave is a scalar of potential energy, right?
Correct.
So basically, I can describe an electromagnetic wave in the same way using only the pointing vector, which says that the energy in the wave varies sinusoidally. And I don't need to talk about the electric field and magnetic field. And I think Ian already pointed this out.
Isn't that the same equation for sound? Was what you're showing there?
Yes, but when you're saying that, you're confusing the physics, two physically different things. And that's why you're getting an objection to it, because you're saying that sound is like an electromagnetic wave. Well, the only thing that really makes them similar is the fact that they're waves.
Well, as Ian points out, is more than that. It's that all of their equations seem to be exactly similar, and the way they behave seem identical.
What's exactly similar? There's no where is there a two-part aspect to sound? I mean, where is there an electric aspect and a magnetic aspect to sound? There's only, there's
no,
only.
There isn't. You see, that's what I would argue, that even though
there's your problem right there. You're trying to describe something that contains two aspects inside of it and compare it and say that's the same thing as something that only has one aspect inside of it.
No, this is actually my point. I'm saying that for a sound wave, you cannot find anything corresponding to a magnetic or electric field. I mean, that just doesn't make any sense. And I'm saying that we should look at the electric field in that same way, and that even though it's called electromagnetic, there is actually no electric and there is no magnetic field. Like I said, there's no experiment that can measure the separate electric or magnetic fields in a traveling electromagnetic wave.
Well, that's very good, but you can't explain polarization. And
I knew that someone would finally get to this.
You can't explain how the electricity gets converted into magnetism and the magnetism converted into electricity, because you say those two things don't exist.
Any
no, those things can be explained
at some point.
I mean,
sorry,
so this is
what was that you were saying?
To my other microphone.
Apparently not.
Paul, go ahead.
Everybody can hear me.
To my bad microphone, so I got a connection, but it's pretty poor sounds.
So, Paul, did you trying to say something? You had your flag raised.
Yeah, I've been waiting. I don't know if you can hear me.
Yeah, we can hear you.
Doesn't work on my computer. I'm on telephone and headphones that I can't hear anything through. So But I have kind of my own model analysis of EM radiation, and I'd like to give it here. Take about 5 minutes if you got time.
Well, we're kind of running short on time for a large presentation.
It's
so
5 minutes.
I don't think we have, because 5 minutes would usually be longer than that. But I'll give you, can you describe it briefly in like a minute? What is your main, what do you think the electromagnetic wave is? Basically answer that
transverse.
question. And, you think it's transverse?
My system explains how it becomes that.
And how does it become transverse?
It becomes transverse because whatever it is initiated in, be it a light bulb or the Earth itself, the beam going up is affected by moving electrons in a light bulb, or on Earth it's by moving electrons because of the rotation of the Earth itself. And that rotation, about 2 meters a second versus 300,000 meters per second, that sideways motion creates little dents in the beam of radiation that is heading straight up, for example, from Earth. And that continuous rotation continually creates the same image for that beam, and you get it dents the beam every so often, and so you have a beam going upward in one direction very fast, and you got the sideways beams that become waves within the beam, and those that fits the whole scale of
But does that agree or disagree with the mainstream's assertion that there's this time-varying electric and magnetic component? It sounds like it's completely different.
Basically,
it's
the same thing.
It's the waves are essentially create the electric, as I had described before. The waves are created in one direction because you get the rotation, say, of Earth hits it from one side, so you don't get the the alternate wave. You get the up and down, not the up and down wave. You get the lateral wave, and so you can look at it like a standard sine wave, which is two-dimensional. You can look at it that way because you have specifically one direction in which the waves are created. When you get more complex out in space or hitting other matter, the third dimension of waves could come into effect, and that's related to the magnetism.
All right, so we're getting close to the end here. I think Bill and Ian want to make a comment. So I'll let Bill and then Ian go.
Okay.
Okay, thank you. I want to point out that the solution to electrodynamics that Oliver Heaviside did, where he only used 4 of the empirical equations instead of all 6, it did not obtain the relativistic effects, the quantum effects, and it did not obtain the longitudinal form of light in addition, or fields in addition to transverse. And but when you solve all 6 of the empirical equations and you don't use the vector potential, but you use the energy potential only, then you obtain all these things. You obtain relativistic effects, what causes quantization, you obtain the emission and absorption of radiation and the radiation reaction. All of that you get directly from the empirical equations of electrodynamics. Those things are missing from these other theories. And I'd also like to point out that you can buy on the internet a light energy measuring device which measures longitudinal radiation.
All right. So, Ian, you had a comment.
Forms, longitudinal.
Thank you, Franklin. I wanted to mention one or two things just before we finished, because we've dealt with most of the concepts. Firstly, I talk about exceeding the speed of excuse me, sound in air and sonic boom and things like that. Well, have we any experimental evidence that the speed of light in the ether, if you like, can be exceeded? And
yes, it can be.
Yes, and I give some of that. So you know this bit because I think we've discussed it before. I talk about the total internal reflection of radio waves via the ionosphere. And I point out that basically means that the phase velocity of the wave exceeds c naught, if you like, in free space. And then you get questions of group velocity and phase velocity, and you can multiply the two of them together, you can get c squared. But that's an experimental evidence of one thing. Now, the second thing that we haven't looked at is in section 4 of the paper, I look at what appears to be a separate consideration: light refraction and light aberration. But I deal with them in parallel. And I basically contend, by just looking at a simple mathematical analysis, the principle of least action in the case of light refraction, and just simple trigonometry, if you like, in the case of aberration, that they're really complementary. And I claim that this explains the surprising result of the Airy experiment, where he changed the refractive index of the medium in the observing telescope, in other words, water in this case, and he didn't get an increase in the aberration angle because they sort of compensated each other. So the reason I think this is important is that I conceive of the special theory of relativity arising in the first place because experiments like the Michelson-Morley experiment, the obvious explanation of that was that, well, the ether was actually carried by the Earth in its solar orbit. And, there was an ether drag through water, observed by Fizeau. It mightn't have been perfect, but it was a drag. But that seemed to be contradicted by aberration, which seemed to show that there was no drag. And therefore they said, we don't understand the theory of drag. The Stokes ether doesn't explain everything. But actually, it does explain everything, because if you look at the case of aberration in conjunction with that of refraction, I claim it would explain that, and it would make, obviously, the theory of relativity unnecessary and the theory of ether drag quite satisfactory in explaining phenomena. So I don't know if there's time to talk about that, but that's an additional point, Franklin.
All right. Well, looks like Cornelius, you had a comment, and you'll be our last comment before I try and summarize.
Can you hear me this time okay or not?
Still a little bit quiet. We can hear you, though. Go ahead.
Okay. Well, my comment was basically that we're talking about the transverse wave and the longitudinal wave, and I've mentioned before that in my view you can't have one without the other. It's just a matter of perspective. Even if you take your simple your speaker that's vibrating back and forth, there is a component to that when you look at it from the edge on, there is a back and forth, a transverse motion at that point. And if you look at a longitudinal wave, longitudinal waves will diverge or spread, but if you look at them from the point of spreading towards you, you will see that they are, in fact, a transverse characteristic to those waves. The other additional point to that is that transverse waves occur at boundaries of, and basically if you look at a longitudinal wave and you create a boundary, an edge where that longitudinal wave is passing by it, you'll get a transverse wave. Also, if you take two longitudinal waves and you mix them together, where they mix, you'll see that what it consists of is a transverse wave traveling along a vector. If you have two spherical longitudinal waves, two spherical point sources of longitudinal waves, and you mix them together, you will see that where they mix together, they create a transverse wave pattern. And so whether you have a transverse wavefront or a longitudinal wavefront, you have both wavefronts in every wave.
Okay, so it looks like Carrie, you had a comment.
If you were to take the raindrop characteristic, or just a drop on the water, and you look at the spherical nature of those waves, and you were to take that focal point of that drop and vibrate it up and down laterally in one direction, you would see that occurred to the wavefronts when you looked at them perpendicular to that was a transverse wave characteristic. So it's really all one and the same thing. It's just a matter of which one has a higher amplitude, higher power. And Bill was talking about the power, and the power has been talked about several times. If you look at a transverse wave, its power wave, which is perpendicular or longitudinal to the vector of travel of the transverse wave, is actually a series of longitudinal waves.
Okay, so Harry, did you have a closing comment? No?
I think we're talking about conceptualizations of a physical idea, and we really didn't talk about what the physicality is. And
well, I would argue that the physicality.
Bob Gray proposed,
I would argue the physicality is exactly the same as sound waves. That's
Bob Gray proposed that.
Go ahead.
Bob Gray proposed that it's energy, as I understand it, and perhaps we could agree that what the wave is conveyance of energy, how energy is transported from one place to another, and perhaps that is something we should be able to agree upon, if anything.
Well, I think we can all agree that perhaps these things are waves. They're like a sinusoidal variation of something, whatever that thing may be. But the question is, what is the electromagnetic wave? We have two possibilities. We have the mainstream's possibility, which is it's this time-varying electric and magnetic field. That is what mainstream thinks it is. And I think we've discussed that particular idea has got a lot of conceptual problems. The other possibility is that we've seen that electromagnetic waves are very similar to sound waves. So the other possibility is that all that mainstream stuff is wrong, and that what we really have here is something which is exactly the same thing as a sound wave. Of course, then you brought up the one thing is that, well, how do you explain things like polarization, for example? And that is the number one motivation for why people are talking about transverse waves, because they think that only a transverse wave can be polarized. And that would be an entirely another discussion. Maybe we should have another discussion just on that, which is, does polarization mean that EM is transverse? And there's always this very naive picture of a rope through a picket fence, and that if you wave it this way, it will block the waves going this way, and when you wave it this way, it'll allow those ones through. I think that's an extremely naive picture about how polarization filters work. And yeah, I would have to explain, if I want to defend the viewpoint that the electric wave is exactly the same thing as sound wave, which is a compression wave in a particulate medium, then yes, I would have to explain how polarization works without there being no transverse component at all. So, I've done stuff like that, but since we're here at the end of the meeting, maybe we'll save that for another time. But I just bring up those two possibilities for the physicality of the wave. That, mainstream says it's this electric magnetic time varying thing. On the other hand, the electromagnetic field looks exactly like sound waves in most every aspect that you can think of experimentally. They seem to act just like a sound wave would, except for this polarization aspect of it. So if you were to ignore polarization, then you would probably immediately say that it's exactly the same thing. But like I said, that will be perhaps a topic of another discussion here. But we have reached the end of our time, and I thank everyone for participating in the discussion about what is the electromagnetic wave. So perhaps we have raised more questions than answers, but that is what we're here for. All right.
Thanks, Franklin.